Welcome, Ride Country Day School. We're going to get started in a minute. So you're going to have 15 minutes to present. I'll give you a 5-minute warning before the end, 2 minutes, and then 1 minute. Just glance over to me occasionally because you'll be mostly focused that way. And then after 15 minutes, we'll do 5 minutes of questions, and you'll have a moment to thank whoever you want to thank. Okay. Let's give it like till 10, because if there are people coming in on the live stream, and then I'll say, and you guys can get started. Whenever you're ready, introduce yourselves first, and then you can get started.
Sounds good. Hello, everybody. My name is Jamin Ding, and I'm currently a senior.
My name is Dana Ballin, and I'm currently a senior.
My name is Alyssa Chu. I'm currently a senior, but I'm sick today, so I won't really be talking.
And my name is Jonathan, and I am a junior.
Good morning, judges, guests, and other competitors. We're Team 18015 from Ride Country Day School, and we're here today to present on this year's M3 challenge problem, hot button issue, staying cool as the world heats up. Our goal with this year's problem was to investigate the effects of heat waves on the communities that have the highest stakes in these crises. Specifically, we wanted to explore the effects of heat waves on the community of Memphis, Tennessee. With that in mind, we were asked to address 3 questions, the first of which is hot to go, where we developed a model to predict the indoor temperature of any non-air-conditioned dwelling over the course of a 24-hour period during a heat wave. We began with 8 initial assumptions, the first 3 of which relate to the initial temperature of the indoors. We began by saying that the initial building temperature starts as the same as the outdoor temperature, and that it does not vary significantly from the outdoor temperature. In addition, we assume that the outdoor temperature stays constant at every point around the building. The next 5 relate to the building's geometry, and we said that the rooms are square in floor plan and equal in size, that the ceiling height is 2.4 meters, that houses modeled are made of wood, that heat enters the houses through the walls and ceilings only, and that the thickness of each of the walls and ceilings is a foot each. We originally given data for the outdoor temperature by the challenge itself, which you can see plotted over here in blue. Going by the shape of the blue dotted points over here, we determined that a sinusoidal fit would be the best way to come up with a model for the outdoor temperature. And so we regressed an equation for the sinusoidal equation, which is shown on the left over there. We found that it had an R-squared value of 0.97, indicating a relatively accurate fit. We then began with Newton's law of cooling as our base model for the indoor temperature, where the rate of temperature change is dependent on a cooling coefficient and the difference between the indoor temperature and the outdoor temperature. We decided that this model would be a good choice because it is computationally efficient and represents the primary mode of heat exchange in this scenario. In addition, it works well when the differences between the indoor and outdoor temperatures are moderate. Since we were able to regress an equation for the outdoor sinusoidal temperature, we substituted that in for T sub s, as shown in the original differential equation over here. We then recognized that this was a linear ordinary differential equation and expanded it, which is shown on the bottom over here. We used this analytical solution and applied it twice to represent the heat transfer from the exterior to the wall and from the wall to the interior. The results of which are shown over here. As you can see, there is a thermal lag, which is to be expected, between the outdoor temperature and the indoor temperature. And the thermal lag ranges between 45 minutes to an hour, approximately. The maximum predicted temperature for each of the homes is around 38.4 degrees Celsius. We then performed a sensitivity analysis on our results to ensure that the model was stable. So we averaged the coefficient of variation over 10,000 trials with an average 5% variation in each of the inputs to mimic real-world uncertainty, and found that there was an overall 5.5% uncertainty within each of the models. This indicated to us that overall, our models were resilient to random error. So our primary strengths were that we were able to use an actual physical model, a widely accepted physical model, to come up with our base model, and we had an analytical solution with parameterized features that allowed us to gain insights into the long-term behavior of our solution. In addition, we had a realistic thermal lag, which was shown in our graphs. However, we did assume a simplified geometry for the buildings, and we weren't able to account for internal heat feedback from the inside sources.
So with the newfound knowledge that temperatures inside a dwelling without air conditioning can reach almost as high peak temperatures as outdoors in a heat wave crisis, we sought to look through the lens of the power companies, who are tasked with supplying the increased energy for people who want to stay cool as the world heats up. So we moved on to the second question, power hungry. We were asked to develop a model to find the peak demand in Memphis's power grid during summer months, both now and 20 years from now. We assumed that there would be no drastic changes to the rate of climate change and that there would be no drastic changes to the population trend of Memphis, Tennessee from the previous 10 years. We also assumed that the monthly electricity consumption of East, South, Central USA would mimic that of Memphis, and that there would be no power disconnects during any given heat crisis. So we started our analysis by finding which factors could best indicate future consumption. We did this by using the Pearson correlation coefficient, with results seen on the heat map to the side. As you can see here, the temperature of the month with maximum electricity usage was the best indicator of consumption, with an R value of 0.77, which is above the generally accepted value of 0.7 for a strong correlation. We then sought to verify this correlation further by normalizing both the average values of temperature in July and August, which tend to be the hottest month, and the average monthly consumption. This time we got an R value of 0.83, which is once again above 0.7, a p-value of 0.0005, which is far below the generally accepted p-value of 0.05, and then a root mean squared error of 0.015. So this justified our correlation. So then, with that in mind, we had the task of predicting the temperature, which we could then use to find the electricity consumption. We chose to use a linear regression model, as shown here, and found that the average temperature would increase around 0.02 degrees Celsius each year. We then looked to further justify that, though, by looking at world temperature data, which also showed a 0.02 degrees Celsius increase each year, and then also the climate.gov estimate of, once again, 0.02 degrees Celsius each year. So now we had to reverse engineer that temperature data to the consumption data. We started with an inverse normalization to find the peak consumption demand, and then we did a proportionality estimate between the eastern, south, central United States and Memphis. This was done using past values for the consumption of Memphis divided by the consumption of the eastern, south, central United States. And then we further verified that by using the population of Memphis and the population of the eastern, south, central United States. And as you can see here, these both got relatively the same value of 0.033. So with this process in mind, we found the average temperature both now and 20 years from now. In 2025, we found a 33.1 degrees Celsius average temperature, and in 2045, we found a 33.6 degrees Celsius average temperature. And these correlated to a 1.04 times 10 to the 9th kilowatt hours and 1.0818 times 10 to the 9th kilowatt hours, respectively, for Memphis electricity demand. So we were able to eliminate unrelated data through statistical analysis, and then we cross-verified results both for future temperature forecasts and for the proportionalities from Memphis to the larger area of the United States, and found that they were all relatively verified. However, we did assume a lack of policy changes, and we had a limited range of data throughout the years for all data points. We would also like to investigate temperature fluctuations each year in the future.
Despite the robustness of these power grids, there are still chances that power grids will fail in the case of a heat crisis. This brings us to problem 3, beat the heat, where we were tasked with developing a vulnerability score for various neighborhoods in Memphis to help equitably allocate resources to different communities in the case of a heat crisis or power grid failure. Our key assumptions were based off of which factors had an influence on the heat vulnerability. We said that a building's shape and size, building material, separation between buildings, which accounts for the urban heat island effect, and the amount of forestry and parks, open space in an area, all had an effect on heat vulnerability. There was also a CDC study done that looked into how socioeconomic conditions have an effect on heat vulnerability due to communities with lower socioeconomic status not having as much access to key resources such as healthcare or cooling during these heat crises. The study also mentioned how elderly people and minors are more vulnerable than working-age adults, and that people who take public transportation or who walk to work are more vulnerable than those who commute by car. So based on these assumptions, we were able to ask ourselves 6 key questions, which we used to determine the features that we want to include in our model. So based on these questions, we found that we want to include open space, housing, income, age, and transportation. And to weight all these features, we use a data-driven method known as an entropy-weighted model. So entropy is essentially a measure of the information gained from a feature, where if you have a high variability feature, like you see in green, you get a low information gain, and thus you have a high entropy. Whereas if you have a low variability feature, you have a high information gain and a low entropy. Because of the higher information gain, low entropy features are generally weighted higher than high entropy features in an entropy-weighted model. To construct this model, we first calculated a score for each feature, and then we normalized these scores for each neighborhood. We then calculated the entropy for each feature over all of the neighborhoods, and then used those entropy values to calculate the weights for each feature. And to outline some of the scoring methods, we did this as follows. So age was taken as the proportion of elderly and young people to the total population. Income was the average income in a neighborhood. Housing was a weighted average of houses built by decade. So if you had a house built 5 decades ago, it would be marked with a coefficient of 5, 4 decades ago with a coefficient of 4, etc. Open space is a measure of the total open space in a neighborhood, and transportation is a weighted average of commuter types. So if you have someone who commutes to work by car, they'll be weighted once, whereas someone who commutes to work by public transportation or who walks to work would be counted twice. So running these weights on our data set, we found the following. We found that income and open spacing had the highest impact on a community's vulnerability score. And using these weights, we were able to get scores for each of our communities and multiply that by the community's population to find our final scores. As you can see, Uptown and Finch District had the highest score, while East Memphis and Colonial Yorkshire had the lowest. Based on these scores, we were able to allocate resources as follows. So half of the resources of Memphis were allocated equally to each community, while the other half were allocated proportionally to each neighborhood based on their score. So Uptown would have the most, and East Memphis would have the least. We were able to create a very strong predictive model using the data that we were given, and we used data-driven methods to derive our weights. In addition to this, we were able to quantify our resource allocation guide for Memphis, where the resources can be interpreted as water distribution or creating cooling centers in different areas with respect to the percentage that we're allocating resources. However, some of our feature hyperparameters could be refined, and there were some features that we wanted to include in our model, such as building shape and size and building material, that were not given, and so we could not really implement those.
So throughout this problem, we sought to look at heat crises first by identifying and understanding the problem itself, then looking into primary interventions, and then finally secondary countermeasures in case those primary interventions fail. So we looked at the first question, which asked us to compare outdoor and internal temperatures. We did this by solving a linear ODE for an analytical solution and then validating our model using the Monte Carlo method. We found that there is a temperature lag from indoor and outdoor temperatures. However, they can reach almost the same extremely dangerous high of temperatures. So with this in mind, we looked through the lens of power companies, who are tasked with supplying the demand of increased electricity during these times of crisis for people who want to stay cool as the world heats up. So we did this by identifying strong correlations using Pearson correlation coefficients. Then we applied a linear regression twice to model future conditions, and then we forecasted the demand of 2045 via scaling. However, as robust as these power grids are meant to be built, sometimes they fail. So we had to then look through government officials who are responsible for taking care of the people when these power grids fail. So we did this by identifying which communities needed resources the most. We identified 5 vulnerability factors and then used an entropy-weighted method to assign weights to these factors. Then we understood these factors and allocated resources proportionally to all of the neighborhoods in need. We hope that the solutions we found to these problems will not only aid city officials and power grid companies in Memphis, but all over the world to help them address heat crises accurately and save the people. Here are references, and thank you so much for listening.
Thank you.
Thank you very much. So what are the questions or the directions you would have liked to have pursued if you had more time to work on this?
Well, first, for our first question, as you can see, we looked at purely conduction as the form of heating through outside and inside. And realistically, there would be people walking around inside. There would also be windows, which would allow for sunlight to come in and kind of like a greenhouse effect, like cars work, where the heat would get trapped inside. So that would also impact the heating, which could actually increase the temperatures even further, which would make it even more dangerous for people inside. And then we also would have liked to look further into the lag between the external and internal temperatures a little bit more, because realistically, the entire wall wouldn't heat up all at once. It would heat up kind of gradually.
Yeah, and then I can talk about my part of the problem. So the third question, sorry, let's just fast forward to that. Yes, so again, for like the data-driven methods that we used, some of our feature height parameters could be tweaked. So that would be like refining, for example, the housing feature, right? We said that the vulnerability of a house was linearly correlated with how old the house was, but perhaps we could like investigate that further to ascertain if that was actually the relation. And then there are some features that we were not able to include in our model that we would like to include if we had more time and more data. And in addition to this, one other interesting application that we could have used for this would be an agent-based model where you can actually simulate the interactions between different members of the community and see how that vulnerability really plays out in like an actual simulated environment.
And I think for the second question, our predictions relied a lot on predicting the temperatures, sorry. And so obviously in real life, temperatures vary and they fluctuate. And we modeled them linearly based on literature that we read, because this is a relatively short-term effect. But we would also like to look into various other models for climate change, and also to look at whether these fluctuations have any periodic or seasonal patterns.
Can I ask a follow-up question on the model 3? So I want to understand these entropy-weighted values more. I don't see how they're related to vulnerability. Like you mentioned it's a predictive model, but are we predicting anything about vulnerability, or is it just a measure of how variable the data is?
Yes, so you're talking about this?
Yeah.
Yeah, so essentially, the entropy-weighted model is basically if you have just this data in a vacuum, and if you don't really have the expertise to ascertain like if a given feature would be more important than another given feature. This is a great data-driven method to actually assign weights to these, because obviously we're not all like experienced in this field, and so we feel like our subjective weighting would be like deleterious to actually creating a good predictor for vulnerability, and so we decided to let the data speak for itself.
But why is a highly variable feature mean that it contributes more to vulnerability?
Yes, okay. So I think there are two things that we need to talk about. So variability as in like the statistic sense, like standard deviation, and then
Sure.
variation between y values as you, for each x value. So if you can see for the high entropy feature, you have, for all of the x values, there's little to no variation in the y values. So that means that the standard deviation of this distribution would be infinite, right? And that means that
But what are the
really
y and x values here? So the x is some number, like some measure about the neighborhood.
yes.
And then what is the y here?
Yeah, so the x is just like the samples, and then the y is the actual feature value. So in the case of income, it would be each of the neighborhoods, and then the income from that neighborhood would be the y.
So okay.
So if you remember also, like Jarnath said before, we don't really have a lot of expertise in the different ways that a community might be affected by each of these values. So in our assumptions, we basically assumed that they would all weigh the same after reading literature. In reality, I'm sure that certain things like socioeconomic conditions would have a higher value and weighting, but that is also biased from my own experiences. And we would like to take our own biases out of the equation. So we read a lot of literature, just finding which would impact communities, and then we decided to look at variation rather than our own biases to add it to a model.
Okay. I'm not totally convinced, but we can leave it. I think it's
Oh,
for
no,
future work. Yeah.
No, I think I can I think I can.
I want to give someone else a chance to ask a question, but I mean, I understand your answers, and I totally agree that it makes sense to try to come up with something subjective, which, I mean, objective, which certainly you did, which is good.
Yes, I do have a question. So in your question one, your answers, your models are very similar for all 4 types of apartments or dwellings. Do you think this is realistic? Or I know you already mentioned that you could consider other factors, but what are those factors and how possibly they will change your model or models, because you have 4 of them?
I'll take this question. So as you mentioned, yes, the heating graphs for these do look quite similar. I think part of that is due to the fact that it's over a 24-hour period, and our thermal delay mainly comes in the form of like a thermal delay between the inside and outside, which happens over the course of approximately an hour, which is why it looks similar. Can you go to the next slide, please? If you go to the next slide here, you'll find that the bigger, like the more volume a building has, the longer it takes for it to follow the outside temperature, which is what we expected for. Can you go back a slide, please? Yeah, which is what we expected for, which is what we expected to happen physically. The other thing is that, like we mentioned earlier, we weren't able to take into account things like, the amount of sunlight coming in through windows, or, what orientation it's facing, or how much tree cover there is, because we thought that was more, because for some of those are more categorical variables, while for others, we figured that not enough data was provided so that we could truly incorporate those into an accurate model. And so in the future, if we were to incorporate those, I believe that it would show more variance in each of the graphs shown here. But for now, this is based on, can you go back a slide? We based our model mainly on the outdoor temperature and conduction from the heat from the outside to the inside.
Right, so did I understand it right? The difference between those 4 apartments or housings is the lag when the temperature heat, but not the maximum temperature. Is that right?
Sorry, yeah. The maximum temperature is different for each of the houses, and I think if we had more time, what we could have done was perhaps find a better incorporation depending on the volumes of each of the houses. For now, the main thing that changed with each of the buildings here was the cooling coefficient. And that is what you see here. I think if we had more time, what we would have liked to do is do a little more research into the kinds of materials used in each of these buildings, because I think bigger buildings will use different kinds of materials. And so the peaks would be a little different.
Okay, yeah, thank you.
Okay, you have a question. You at the very end, you discussed your Monte Carlo simulations. And you talk about varying your data points. I was wondering if you could expand on that, give us some more details about what that means and how you did the calculations and what insights that gave you.
I'm sorry, could you repeat the question? I couldn't hear it that well.
Sorry, you for your Monte Carlo simulation for the first question, you said you used 10,000 data points, or 10,000 trials. You varied the data points. And I was wondering if you could give more details about what data points you varied and what insights you got from that.
Yes, okay. So could you go back a slide for a sec? Yeah, so the main things that were taken into account here were, the outdoor temperature, as well as the cooling coefficient, as well as, can you go back a few slides to the one where we did the regression? The one before this, yeah, before this. No, before this. Yes, there. As well as the parameters for the outdoor temperature. So we added random variance into those to model like real world uncertainty and random error that could occur, just from the real world being not as certain as it would be in a model. And so what we're trying to show is that even if we add in random error over the course of many different trials, that our model will stay resilient and not show an extreme amount of change from a small amount of change in the input.
Could you give some more details about how you added that jitter?
Sure, yes. So we have an original value set here for, we have original values set for each of the parameters we inputted here. And to those, like I mentioned earlier, we added a 5% like variance to each of those. So depending on what the parameter was, we took 5% of that and either added or subtracted somewhere in the range of like plus or minus 5% of that, and used that as the new input for each of the trials.
Okay, awesome. Thanks, guys. Let's all thank the team. And then if your representative wants to say a few thank yous, now's the time to do it.
I'd like to begin by saying a big thank you to our coach, chaperone, and math teacher, Mr. Mineo. He's our wonderful math teacher at school, and we really like to thank him for putting up with all our shenanigans in class. And on behalf of all the seniors on our team, we will miss you dearly as having you as our math teacher. Next, I'd like to take some time to thank, the people who really brought us here. So our parents and our families who provided us support through every step of our journey on the way here. We'd like to give you all a big, big thank you for helping us get where we are today. Last but not least, I'd like to thank the hosts and sponsors for today's event, namely MathWorks, SIAM, and Jane Street. On behalf of the team, we really enjoyed, being able to do math modeling and being able to participate in a wonderful event like this. And so we'd like to extend a huge thank you for making this possible. Thank you.